Hi everyone, welcome to my channel. In today's video, we'll talk about Newton's law of cooling and solve some problems regarding that. In daily life, we observe that a cup of hot tea becomes colder after being kept at room temperature. And there are several this kind of incidents happened in our daily life. Okay, so let me put it in general. Suppose we have an object which is hotter or cooler than the ambient room temperature. And we want to know how fast it cools or heats up. The Newton's law of cooling gives us the answer. It states that the rate of change, the rate of change of temperature of the body is directly proportional to the difference between the body and surrounding. So let me write it in mathematical way. So suppose T of T denote the temperature of a body at time t, and Ts denote the temperature of surrounding. Then, by the Newton's law of cooling, rate of change of temperature, which is dT by dt, is proportional to T minus Ts, which is the difference of the body and the surrounding. Okay, so if we solve this equation, then we have dt is nothing but k times T minus Ts. But T is the constant, so we can write it as dt by T minus Ts is k times small dt. Okay, so take integral both sides. So we have ln T minus Ts is equal to kt plus ln C. So we are taking ln C for simplification of the calculation. So we have T minus Ts is nothing but C times e power kt. So T of T is nothing but Ts plus C power kt, which is the temperature at time t. Now, try to understand this kind of problems by an example. Okay, so the problem is a body at temperature of 50 Fahrenheit is placed outdoors where the temperature is 100 Fahrenheit. If after 5 minutes the temperature of the body is 60 Fahrenheit, then we have to find how long it will take the body to reach temperature of 75 degree Fahrenheit. And the second problem is the temperature of the body after 20 minutes. Okay. So here we have given that the body at a temperature of 50. That means the initial temperature T of 0 is nothing but 50 degree Fahrenheit. Okay. So is placed outdoors where the temperature is 100 Fahrenheit. So that means that surrounding temperature is Ts is 100. And another thing is given that after 5 minutes, the temperature of the body is 60 Fahrenheit. So T of 5 is nothing but 60 degree Fahrenheit. Okay. So by the Newton's law of cooling, we know that this dt is K times T minus Ts. And here Ts is 100. So it will be K of T minus 100. Now try to solve this problem. dt by T minus 100 is K dt. Now take integral both sides. So we have ln T minus 100 is kT plus ln C. So we get T minus 100 is C e power kT. Now, initial condition is T of 0 is 50. So by putting this, we get 50 minus 100 is C e power 0 times T, which is nothing but 1. So C. So C is, we get minus 50. So the equation will become 3 minus 100 is minus 50 e power kT. This is the general formula. Now we need to find K also. So another condition is given that after 5 minutes temperature is 60 degree. So that means T of 5 is 60. So if we put 60 here, so we have 60 minus 100 is 50 times e power 5k. So that means minus 40 is minus 55k. So we get e power 5k is nothing but 40 by 50. So 5k is ln 40 by 50 and k is ln 40 by 50 by 5. And if we calculate this, we get this will be minus 0.045. So we get k. So the equation becomes t minus 100 is nothing but minus 50 times e power minus 0.045 t. So t will be 100 minus 50 e power 0.045 t. So now look at the second problem, the temperature of the body after 20 minutes. So we need to find what will be T of 20. So 100 minus 50 times e power minus 0.45 into 20. And if we calculate this will be 79.671 approximately. Now the first question is remaining. The first question is how long it will take the body to reach temperature 75. So suppose it will take T0 minute to reach at 75. So that means T of T0 is 75. So that implies 75 is 100 minus 50 times e power minus 0.45 T0. So it will be minus 25 is equal to minus 50 e power 0.45 T0. And if we calculate this T0 will become ln half by 0.045. So this will become 15.4. So after 15.4 minutes, this will reach to 75 degree temperature. So that's how we solve this kind of problems.